Good morning, everyone, and welcome to this third episode of our Axiom Optics Microscopy webinar series. Today, we are partnering with abbelight, and we are going to introduce you to the SAFe RedSTORM system. Today's talk is entitled Entering the Nanoworld and Imaging 3 Colors with 1 Laser. I'm Vincent Prenod, Sales Manager at Axiom Optics, and here is also Cindelia Guillaume, Application Scientist at abbelight. Hi, Cindelia.
Hi. Hello, everyone.
So here's today's outline. I'm going to start with a very brief introduction of Axiom Optics and abbelight. And then I'm going to give the hand to Cindelia, who is going to introduce you to abbelight technologies and introduce you to the SAFe RedSTORM system highlights and application examples. Then Cindelia is going to give you a demo of the SAFe RedSTORM, and she's going to show you how, with that system, you can image 3 colors simultaneously with 1 laser. And then we're going to have some time for question and answers. So this gives me the opportunity to tell you that if you have any questions or comments during the talk, there should be a chat window on the right of your window, and you can post any comments, any questions. We'll answer them at the end of this webinar. Also, if you have any issues hearing us or seeing, just let us know. And if everything is going well, then feel free to let us know as well. So let me start with the introduction of Axiom Optics and abbelight. Axiom Optics is a company specializing in high-end optical instrumentation. We have a microscopy division with 3 people working in this division: Philippe Clemenceau, the co-founder and CEO of Axiom Optics, Lauren Vincent, our marketing specialist, and myself, sales manager. In our microscopy division, we offer high-end microscope add-ons or microscope systems that will basically increase the add a new capability to your current microscope. So, for instance, we partner with confocal.nl. We offer the Rescan confocal microscope, which is a laser scanning confocal system plus super resolution. We also offer the LIFA toggle film system from Lambert Instrument, which is a camera-based frequency domain film system. It's a very good system for film and fret applications requiring extra speed. In single molecule localization microscopy, we work with 2 companies, abbelight, that we will present today, and Imagine Optic. Imagine Optic is specializing in adaptive optics components and systems. They have a system dedicated to single molecule localization microscopy. It will not bring you dSTORM on palm capability. You need to already have this capability, but if you do, you can then increase your localization accuracy with that system. And then we also partner with Imparadox and their SensoCell optical tweezer and force measurement platform, which is mostly used for mechanobiology. So if you have any questions about any of those systems, feel free to contact me. I'll also contact you back after this webinar, so you will have my contact info. I'll be happy to help you. Let's now talk about abbelight. Abbelight is quite a big company now, but at the beginning, it was 4 founders, 2 from the academia, so Cendric Levesque-Fort and Emmanuel Fort, and then Nicolas Bourg and Jean-Baptiste Marie, who are respectively the CTO and the CEO of abbelight. The goal of abbelight is really to enhance the complete workflow of single molecule localization microscopy, from helping you with sample preparations to imaging, and then also to analysis. So to give some examples, for instance, they offer services and devices to help you with your single molecule localization microscopy workflow. They have a bunch of different protocols. They offer samples, reagents, buffers for your imaging needs. They also, of course, offer different hardware solutions, like the SAFe 180, the SAFe 360, and the SAFe RedSTORM that we're going to discuss today. Those could be add-ons that you add to your regular wide field microscope, inverted microscope, but it could also be a complete turnkey system. Then also comes the software. So they offer the Neo software, which is a software for both acquisition and also visualization and analysis. So they have a bunch of post-processing options like clustering, demixing, tracking. We're not going to present everything today, but again, if you have any questions, feel free to contact us. This is just to highlight what I was saying right before. So they offer, for instance, the SAFe reagents. Here you have the 3 different hardware systems they have: SAFe 360, the SAFe 180, and the SAFe RedSTORM. And then the software, there is a video here which is not playing, but basically you can see the acquisition with the single molecule blinking. The processing, we don't see it because it's a video and it's not playing here for some reasons. But you could see the post processing data sets and then the analysis. Abbelight is a French company. They're based in France. I do have a French accent, but I'm working for Axiom Optics. I'm based in the US. We are partnering with Abbelight to sell their solutions in the US. So if should you have any question, again, feel free to contact me. And with that said, I'm going to give the hand to Cindelia, who is going to introduce you to different abbelight technologies and to the SAFe RedSTORM. Cindelia, the stage is yours.
Thank you. Okay. So hello everyone, and thanks Vincent for the introduction. So I'm Cindelia, product specialist at abbelight. And abbelight is a French company specialized in single molecule localization microscopy to reveal a structure at the nanoscale. And today I'm going to present you how to obtain 3 colors with 1 laser. But first, I will start by the theory about the nanoscopy. So what does it mean, nanoscopy? So here you have a standard fluorescence image. It's actin in COS7 cells, and you can guess some structure, but not really actin network, because you need to go behind the diffraction limit. And to overcome of this diffraction limit, there are many techniques, like a super resolution technique and nanoscopy technique, like a STED, stimulated emission depletion, which based on the depletion of the fluorophore in entering regions of the diffraction limit spot. And we have a SMLM, single molecule localization microscopy, is based on the photo switching of the fluorophore, but I explain you just after. So when you use a nanoscope, you can appreciate more details about the actin network. And how can you go behind the diffraction limit? So briefly, the fluorescence principle. So when you observe a point with your microscope, you obtain a spot. We call this point spread function. And when you observe 2 points, you have 2 spots. And this image is resolvable because their spots are distinct. But if you observe 2 closely points, their image is not resolvable because you have the overlap of the spot. So if you want to observe 2 points, their image is resolvable if their separating distance is higher than 200 nanometer in lateral and 600 nanometer in axial. In SMLM principle, it's different. It's based on the photo switching of the molecule. So when you have 2 points, one molecule emits a fluorescence, and after that, another molecule emits a fluorescence. So we can distinguish 2 closely points and to overcome of the diffraction limit. Experimentally, you have a stochastic emission. You have the fluorescence of only a subset of molecules at the given time in order to detect and localize each of them individually. And after, you can reconstruct a super resolved image. So here you have a video of the live stochastic emission. So this is a blinking. And on the right, you have the live reconstruction. It's again an actin network. And when you accumulate the spot, you can reconstruct a super resolved image. There are many techniques in SMLM. You have the STORM for stochastic optical reconstruction microscopy. So we use an organic fluorophore and photo switching buffer. In standard fluorescence, when you excited your molecule, all molecules go in the excited state. And when they go back, they emit the fluorescence. Here, in STORM, we use a photo switching buffer. So we exploit the photochemical property of the fluorophore to send the molecule in the dark state, and only a very small population go back on the ground state and emit the fluorescence. You have the PALM for photoactivation localization microscopy. Here we use a photoactivation or photoconversion protein, and 2 lower laser power, 1 readout laser, and 1 laser to convert state. And we have the point accumulation for imaging in nanoscale topography. Here we use a reversibly binding probe, so the molecule emits the fluorescence when they are attached to the protein of interest. So now I will explain you how to obtain the single molecule imaging, but you know several parameters need to be optimized to obtain this single molecule imaging, like a sample preparation, software, hardware. And this is exactly where abbelight provides a complete solution to bring the single molecule localization microscopy to researchers. We provide a safe reagent for sample preparation, the safe instrument for imaging, and software for data analysis. abbelight provides a safe reagent like a toolkit for STORM imaging. These toolkits are compatible with around 20 commercial dyes and are both adaptable for adherent and not adherent cells. And we provide also a safe sample for calibration and training. For safe instrument, we have 3 instruments: SAFe 180, SAFe 360, and SAFe RedSTORM. They are both adaptable to any invert microscope, offering imaging modality like PAL, STORM, paint, single particle tracking, TIRF, and multicolor imaging. And to exploit the data acquired, abbelight developed a Neo software. It's a user-friendly and robust software to acquire the data, process, and analysis. So now I will focus on imaging and some challenge in SMLM. So how to obtain a 3D information, how to obtain a large field of view as in wide field microscopy, and how to perform the multicolor imaging. So first, how to obtain a 3D information. There are many techniques to obtain 3D information. abbelight uses astigmatism. It's a deformation of the PSF. So when you change the focal plane, you change the deformation, and this deformation gives an axial information. But this technique is limited by the localization precision in X and Y, because when you deform in one axis, so here in Z axis, you deform too in the X and Y axis. So a compromise must to be found. abbelight designed a dual camera system, so we can split the light in 2 paths. In the first pass, we can extract the X and Y position, and the other pass, we can extract the Z information. So we can use an enhanced astigmatism lens we can obtain 1.2 micrometer capture range, and we don't lose the lateral resolution. So now let me show you how we can. Let me show you the image of the mitochondria. So here it's a mitochondria label with a TOM 20. So on the right we have a wide field image. On the center, the 2D STORM nanoscopy, and thanks to the astigmatism lens, we have the axial information. And here you can see the video of the mitochondria in 3D. Okay, so now how to obtain a large field of view as a wide field microscopy. So the standard laser excitation for the SMLM imaging, we use a Gaussian beam centered on the camera. So when you use this laser, we can obtain only 50 by 50 micrometers square. And abbelight developed a new technology. We call this method ASTER, adaptable scaling for top at excitation rendering. So we are going to scan all the field of view of the camera, and we can obtain an homogeneous illumination. And now abbelight can obtain 150 by 150 micrometers square. And thanks to the Aster technology, we can accelerate the acquisition. For example, if I reduce the size of the camera detector, if I reduce the scale, around 20 by 20 micrometer, we increase the irradiance, so we increase the blink, and we can obtain a fast acquisition, around 400 frames per second. But I explain you and I show you during the demo. So now, how to perform multicolor imaging? So this is a conventional sequential multicolor. For example, I would like to acquire two structures actin in Alexa 647, another structure, tubulin, in Alexa 555. So we need to do a double staining. We need use two lasers, 640 nanometer to acquire Alexa 647, and the other laser, 532 nanometer laser, to acquire Alexa 555. And when you do that, you need to correct the drift correction. You need to correct drift, chromatic aberration, and the resolution between both colors. So to summarize the limits for sequential multicolor nanoscopy, we have the different fluorophore photo-switching characteristic, the chromatic aberration, the drift between the color recording, and the time for sequential acquisition. And abbelight focus on only one color, here far red, and we call this the spectral far red demixing. So, for example, I would like to acquire two structures in the neuron, adenosine in Alexa 647 and beta spectrin in CF6080. And we need only one laser, 640 nanometer laser, to illuminate and to obtain the two structures. But the question here is, how can you distinguish the two structures? It's the same. We also use a dual camera system, and we put a dichroic cube, and now we can distinguish the two structures because we use we measure the difference intensity ratio between the two cameras. So now I will explain how to obtain a multicolor nanoscopy with one laser, one buffer, and one acquisition. And this technique is also possible with a three-color. You just need to add another fluorophore, like a CF660. So here you have the image, the 2D nanoscopy image with clathrin, with Alexa 647, mitochondria with a CF660, and the tubulin in CF680. Okay, so now I will show you a video of this acquisition using a SAFe RedSTORM. It's our new product dedicated for the multicolor imaging. Okay, so now let me show you the video of the demo. Okay, maybe Vincent, you can.
Yes, let me do it.
Okay, thank you.
Here it is.
Yes, thanks. Okay, so here you have our software. So the first, you can create your project. So it's not really clear. It's blurred. The video is blurred. Sorry. Maybe I can share my.
It's good on my side.
Okay. Okay. Good. So the first, we create your project. Maybe a demonstration with a date, and we can change the past project. And after that, you can click on new experience. So new experience for new sample and new cell zone. You click on new cell zone. So new cell zone for new region of interest within the sample. Okay, so now I go to imaging. I click on the setting and start preview. I put little bit laser, so 640 nanometer laser. And here you have a green square. So this is a region of interest. And if I scroll, we can observe the different view, camera 1, camera 2, region of interest 1 and 2. On the right, you have the setting for the acquisition, excitation with the scale and the different illumination mode, TIRF, ILO, and AP. You have a different, you have the processing with parameter for spectral demixing. So here we choose Alexa 647 and CF680 because the sample is a clatrine in Alexa 647 and the tubulin in CF680. So now I will choose my cells. Okay, maybe here. Okay, here is not really dense. You can see a tubulin and clatrine, maybe on the top. Okay, here is good. Okay, you can see a clatrine and tubulin on the camera 1. Here you have the region of interest 1 and the region of interest 2, the different view. And you can observe now the difference between the two camera. So in the first camera, you can observe more clatrine, and the second pass, you can observe more tubulin. So in the first, in region interest 1, you can observe the clatrine because it is labeled with the Alexa 647. And in the region of interest 2, you can observe more tubulin because it's labeled with the CF680. And now I can show you the Aster technology. So I reduce the scale. So here I adjust the scale to my region of interest. I increase the laser power, and you can observe the blinking, so the live stochastic emission. Okay, here you can observe the blinking on the region of interest. I adjust the scale to obtain a homogeneous blinking in all my regions. Okay, maybe here, it's good. I increase the power laser. I adjust the scale. Okay, good. So now I can change the illumination mode. Here you have the TIRF, high-low, and happy. And you can observe that the high-low is the best choice because the signal-noise ratio is better. So I put high-low illumination. Okay, great. So now I can start the acquisition. Before I change the exposure time, I put around 30 milliseconds. I reduce the scale. Okay, it's good. So now I click on start. So I acquire. Okay, cool. So now I acquire the whole molecule here. So in the square below, you can observe the molecule detected and localized by our software. So you have different view. So the molecule detected and only the region of interest. So you can observe the pixel. So here you don't have the deformation of the PSF. It's a 2D acquisition. So now we can observe the intensity ratio. So you have two peaks. One peak for Alexa 647 and the second peak for CF680. And you can observe the difference between the distribution, because in this region of interest, you have a lot of clathrin. You have more clathrin than tubulin. So this is the difference between the distribution of the peak. And now I can show you the live reconstruction of 2D nanoscopy. So here you can observe the tubulin and the clathrin in the same view. And now you have another view. We demix the two color. So in purple you have the tubulin, and in yellow you have the clathrin. So here it's just an artifact, maybe an aggregate of the dye. So now I can show you if I turn off the clathrin, so I turn off the Alexa 647, you can observe only tubulin and any clathrin in this view. So the ratio range that I put in my process is good, because you just reconstruct only a tubulin here. And now I can do the same for the tubulin. If I turn off the CF680, you can observe only a clathrin in yellow. And here you can observe the drift correction in live. So here you have the two peak, and the two peak you don't have you reject the molecule in crosstalk here in blue. Okay, so now I can show you the different views. So it's possible in live to observe only Alexa 647 and only a CF680. And when you zoom, you can observe all view zoom in. Okay, so this is what do you do with our software, and you can observe different parameters in live, like drift, intensity ratio, the localization by frame, and the number of the frame, and the number of photon by frame. Sorry. So in purple, you can observe the CF680 and the black Alexa 647. So now I stop the acquisition and I show you the fast. I can show you the fast acquisition. I reduce the size of the camera detector. So I put 5 512 by 512 pixel. Okay, so now I turn off the laser. Okay, now I can show you the fast acquisition. So now we acquire in 30 frame per second. I reduce the scale and I change the region of interest, the size of region of interest. I can reduce the scale, and now I can change the exposure time. So I put 5 milliseconds. So you can observe the blinking rate increase. I adjust the scale. Okay, so now for 50 by 50 micrometers square, we are in 200 and 200 FPS. We acquire 100 frame in only 7 minutes. So you can observe also the nano 2D demixing.
Just to quickly correct, it's 60,000 frames in a couple of minutes.
Okay, sorry, but it's blurred my computer, sorry. Okay. Okay, so now it's the same. You can observe the different view, Alexa 647 and CF 680. And the same, you have different graph during the live during the acquisition, drift, intensity ratio, localization by frame, and the number of photons by frame. And you also observe the reconstruction of the clatrine and tubulin. So the different view, you can observe your range intensity, the intensity ratio range. So here you don't have the overlap of the two view and the two structure. So now I can stop the video. Okay. So now I can stop the acquisition. I click on Start Preview now to go to change again the size of the. Okay, I change the region of the size of region of interest. I change the size of detector, the camera detector. So I put 256. And now I can change the exposure time. I put 3 milliseconds now. And now the frame per second is around 300. Okay, so now I start the acquisition, and now you can observe the blinking rate is increased, and we can acquire the same image in 3 minutes. And you have also the different view of the clathrin and tubulin. So here in yellow, you have only a clathrin, and you can observe the reconstruction in live. Okay. So now I will show you how to obtain here 2 color, but it's already possible to 3 color. And I show you the Aster technology and fast acquisition. Okay. This I put again a last parameter. Okay. Okay, this finish for the demo. Thank you.
Thank you, Cindelia. It was super nice. So, and yes, just to clarify, this was 2 color simultaneous with 1 laser, but we can definitely do 3 colors.
Yes.
The only difference is, well, the idea is you get on one camera, you get a fluorophore with intensity 75% and 25 on the second camera.
Yes.
And then another fluorophores with the opposite, 25 on the first camera and 75 on the other camera.
Yes.
And with three colors, then you get another one, which is right in the middle of the dichroic with 50% on one and 50%.
Yes.
Cool. We had a couple of questions. So the first one was from Day. He was asking about the sample preparation that you did for this imaging, and I asked more information about what he wanted to know. He asked about if you did any kind of special glass cleaning or cell transfection or fixation procedures. Basically, was impressed by the very low background.
Okay, so for the sample preparation, you need to use a cover slip adapted for the STORM imaging. So adapted for your objective. So a little bit thickness is around 1.5 maybe. I can send you the reference, but is a cover slip adapted for the STORM and adapted for the objective. So 100x turf. And for the label and the fixation, it's like a confocal, but you just need to optimize the labeling for the STORM. So reduce your dilution of your profile.
And this gives me the opportunity to repeat again that abbelight has a very great expertise in sample preparation. So yes, should you need any help, you can contact them and they can advise you. And again, also I guess the high-low and the turf helps getting a very high SNR.
Yes.
There was another question from Joe regarding the camera technology we can use with the system. So I think for the demo, it was the SCMOS, correct?
Yes, SCMOS.
Okay, but we could also use the MCCD. I think
yes,
yeah, go for it.
Yes, is the application and the biological application, but the CMOS is better for do a fast acquisition or for STORM imaging.
Yeah, and I guess you get I mean with 100x or 60x objective, then they have a good pixel size.
Yeah.
For that as well. So Joe again is asking if the cameras are part of the system. So I'm not sure I understand your question. The system the SAFe RedSTORM is basically the illumination module and the acquisition module, the red box that we saw earlier. And then you need to add 2 cameras. When we do the installation, we make sure to align the cameras properly. So
Of course.
yes, but the cameras don't come already assembled on the system. That's the question. If you have any other questions, that's the time to ask them, because in a couple of minutes we will wrap it up. Okay, no more questions. One more question. So Joe again asking, does the system take advantage of the 4 or 5 laser to increase blinking?
What?
Does the system take advantage of the 4 or 5 nanometer laser to increase the blinking? So I guess that's
to have a good blinking. The laser 640 nanometer is better, and the buffer it's adapted for this blinking. It's a answer of the question or not?
I'm not sure. I'm not sure I fully understand the question either. Just so if you want to specify, please go for it. And then Valentine is asking if you tested a new fluorophore, so the CF647. I don't know if you're familiar with that one.
Yes.
Cindelia.
Yes, we can also use the Alexa 647, CF647, CF660, and CF680. So this is a 4 fluorophore that you use for the far red demixing.
Have you found that the CF647 is better than the Alexa fluor?
It's a little bit better because the range ratio is a little bit
sharper.
Little bit high. Yes.
Yeah.
So it's better for the crosstalk.
For the demixing, especially for the demixing.
Yes.
Okay.
And for answer for the last question, so to increase the blinking, you can use the laser in UV, so the 405 nanometer. Yes, but it's just a pulse. So, but in this module, you have just only one laser for the SAFe RedSTORM. So normally you don't need to use this UV laser because our buffer and our laser is adapted to obtain a good blinking.
Yeah, Joe. So just to clarify, the SAFe RedSTORM, so the system we presented today is kind of a niche system dedicated to 3 colors with 3 colors demixing basically. So it's only using the 640 laser.
Yes.
The SAFe 360 that we are going to have at the physiology course is the most modular system, and you can do that, but you can also use 405, 488, 561. And you can use the 405 to reactivate the fluorophores.
Yes.
Okay, so I think we're good. Unless there is a question that comes up right now. If not, then we're going to close this webinar. But if you have any more questions in the future, just feel free to reach out to us, and we will send an email in a couple of hours or days with this webinar, with this recording. And feel free to get back to us if you have more questions at that time. There is another question actually from Valentine, which is which I think is very interesting. If we have ever considered a stripped down version, so basically just the SAFe RedSTORM with no laser, and as this as an upgrade to, for instance, an Nikon N-Storm. So you have an Nikon N-Storm, you have the laser, and then you just use the laser from the N-Storm for your laser. So can we? Do you know if we can do that?
Yes, we can do that. you can use our laser to do a spectral demixing, spectral demixing using the SAFe RedSTORM. And when you use your microscope, so your Nikon N-Storm, you just use our laser, and you can do.
But can you use another laser? Can you control another laser than the Oxus one?
Another, like not Oxus.
Yes, correct.
Another. Normally no, but I can.
Valentine, let's get back to you on that front.
Yes, maybe it's not really possible now but it depends of the laser. It depends.
Okay, so we'll get back to you, Valentine, on that front. Awesome. Well, thank you so much for attending this webinar. And we're doing those webinars pretty much every month. So if you are interested in learning about new technologies, feel free to follow us. And the next one will be about abbelight and those quality assessment devices. Thank you so much.
Thank you.
Have a good day. Bye.
Bye.